Today I will be talking about Dinic's algorithm, coding up a full C++ implementation, and also using that implementation in an online Maxwell problem. So first let me talk about Dinic's theory. Dinic is based on the premise that we want to reach nodes using the smallest distance possible, where the distance is defined as the number of edges between two nodes. That kind of graph is called a level graph. So one aspect of DFS or of Dinic is performing a BFS from the source to the destination to check first if there's any flow possible at all from the source to destination, and also to construct the level graph at the same time. We assign levels to every node, where the level of a node is, again, the shortest distance from the source to the node. Once that level graph is constructed, we send multiple flows, multiple DFS pathfinding calls to find a valid path between source and node. Keep in mind that there are multiple level graph reconstructions, and there are also multiple DFS calls throughout the whole algorithm. This is better than a lot of other popular Maxwell algorithms because it basically looks for batches of augmenting valid paths at once instead of looking for individual paths at a time. The runtime is the number of vertices squared times the number of edges. So I'll get into this code, this boilerplate code that I've laid out, starting with the graph implementation itself. It's an adjacency list that's indexed by a node value, and those node values are indexed by 0. So the value after indexing to 0 is going to be an adjacency list, which is a vector of edges, which is pretty self-explanatory, but the edge struct might be a bit complicated, so I'll explain that. Next node, again, just tells you what the next node you're pointing to, and those are all indexed by, remember, all nodes are indexed by 0 to the number of nodes minus 1, right? So it's going to be one of those values. Reverse index will help us will give us the index of the next nodes, this next node adjacency list, which points to our current node. So whenever you pass flow through an edge, you want to reduce the flow of the back edge. So whenever you do that, this reverse index is going to give us the edge index of the next node's adjacency list, which points to our current node. That's a bit convoluted, but hopefully, if you don't understand it now, it might make more sense when I start filling out the code and actually using it. Our flow is the current flow that has been passed in to an edge so far, and cap is the capacity of the flow being passed in. So again, like I said previously that we're using a level graph, right? We have a level graph, a level vector, which will allow us to index what the level is of a node based on like the node's value, and that's really self-explanatory. It is a global variable, so we will have to refill level to a specific value during each iteration of like a BFS call. So let's start with an add edge. Whenever we're going to add an edge, we're going to add it for the forward edge and the back edge, because whenever you augment the forward edge, you have to augment the back edge. So we might as well construct the back edge right here. So let's create the edge forward, which is going to be equal to the forward, the next node, reverse index, flow, and cap. That's the order of those parameters. So for the forward edge, we're going to do next node and a reverse index. Again, reverse index is kind of complicated, but hopefully this will make sense. I'm going to put in the value right now, and then I'll explain it after I finish this function. So this is going to be equal to the next node.size. This is 0 because there's been 0 flow through this. We've just constructed it, right? So it doesn't make sense. It should be 0, and the capacity is the weight. We're going to do the same thing with the backward edge, except it's going from the next node to the previous node. And it's going to be equal to the prev node.size with flow 0 and weight as the capacity. Now we have to add these to each node's corresponding adjacency list, right? So let's get our previous node and push our forward edge into that adjacency list. And let's do the same thing with our next node. This is going to be the back edge. So, okay, now hopefully it might make sense why we're using this reverse index, but I'll try to explain one more time. This reverse index currently is 0. Let's say that there's no adjacency list at all. The adjacency list for the previous node is empty, right? We're using this so we can figure out the back edge back to our current node, right? Or the next node. So what we're going to end up doing is, because we're going to push these edges to the adjacency lists, we know that the index of these entries is equal to the size before we add it, right? So that's why we're initializing it to graph next node.size and graph previous node.size, because we're going to end up pushing into this index regardless. So it's just a really easy way to figure out where the back edge is and how we can index it really easily. And that should be it for the add edge. So now we can do the BFS function. Remember, the BFS function has a few different capabilities, right? We use it to first check if a valid path exists at all from source to node, and we also use it to reconstruct the level graph every time. We have a global vector for holding the level values, and since we're going to be calling BFS multiple times, we have to make sure to reset it. So we can do that as the first step. We're going to fill the level as an arbitrary value, and we'll do it as -1. And initializing it to -1 will help us later on during our BFS. So now again, we're going to do a BFS search from the source to the destination node. So we can start with a really simple BFS implementation. We're going to also initialize the node for source node to 0, because that's going to be the starting, right? And we just do a normal BFS implementation. So this is going to be the front of the queue, the one that we just popped, and we're going to go to every edge that current node has in its adjacency list. So we can do that by indexing it in the graph, and we can now retrieve these edges, right? So let's get our current edge as this graph current node at this index, and we can get the next node value from the current edge right here. Now, there are going to be two conditions we have to check in order to actually make the connection in this level graph. First, we have to make sure that we haven't seen this next node already in a previous BFS cycle in this same while loop, right? So this is where filling in level as -1 helps us out. Instead of having a separate visited set, we can simply check if this level is already -1, then we haven't visited it yet. And if it is greater than -1, which means that it actually has a level, we have. So we don't want to repeat that, right? So that's our first condition. If the level of our next node is equal to -1, that's good. Our second one is making sure that this edge that we're looking at, right, does have room to send flow through. We're not removing edges that have capped out completely from the adjacency list, but we do still have to check that there is available flow. And we can do this really simply. We just have to check that this flow is less than the capacity, which means that there's room for more capacity to be sent through, or more flow to be sent through. If both of these are met, then we can set the values for these. The next node is obviously going to be the level of the current node +1, and we're going to push this node onto the BFS to propagate the BFS. So cool, that should be good. And yeah, I think we can go ahead and start the DFS now. Let's see. So yeah, our DFS, oh, actually one last thing. Remember that a BFS is going to tell us if we have found an actual path through this BFS from source to destination, right? So we need to return our Boolean value. And we can simply check our visited set. If it's equal to -1, we haven't found an actual path. And if we have a path, that means the level is greater than 1. So we just have to make sure that the level of the destination is not equal to -1. And now we can do our DFS function. After we figure out that there is some valid path, we use the DFS to find a single path at a time. So let's, and we're going to do this recursively. So let's have the base case for the recursive call, which is where our current node is equal to the destination node. If it's equal to the destination node, we're going to return the current min flow. The current min flow is going to be the current and minimum flow that you have seen so far in your recursion trace, right? Like whenever you pass flow through an edge, it's going to be limited by the minimum amount allowed by any edge. So we just store that value in this variable. Now we can go through all of the adjacent nodes of this current node and perform a DFS and see if we can see a real value. So we can do that with this graph to get all the edges, and we can access an edge like this. Cool. So we have to make sure of a few things, right? Remember, we can only perform a DFS to another node if the next node's value is a level up, only one level up. And we also have to make sure that this edge's flow has not capped out. So we have to make sure that the level of the next node is equal to the level of the current node plus 1. And the edge's flow is less than the capacity. If so, we need to find the minimum flow that we're going to pass in to the next DFS call. It could potentially be the same, but if the amount of flow left on this edge is smaller than our current min flow, we need to update that value. So our next flow is going to be the min of our current minimum flow, and the amount of flow that we can send in this edge, right? Which is going to be equal to the current capacity minus the flow. Because that's the amount we can send through. That's going to be the max amount we can send through, right? So now we can call our DFS and see what the value returns. So I can call that DFS function on the next node with the destination node, the next flow, and the graph. So I guess I can put it here. If we never find an actual path, we're going to go ahead and return 0 for this DFS call. But if our DFS val is greater than 0, which means it has some flow allowed to the network, we have to do a few things. We need to first increase the flow of each edge in that path, right? So we first want to increment our flow by this DFS value, but we also need to decrement the flow of this value. We have to decrement the flow of the back edge, which is where we use our reverse index. Remember, because this is going to allow us really easy access to the back edge. So let's go to the next node, and we want the reverse index, right? It's just going to be the reverse index dot flow. And because we're increasing the DFS value of the forward edge, we have to decrease it of the back edge. That's how the flow would work. And that's the dot flow. And we need to propagate this to our previous recursion calls that called this function. So we have to return the DFS val. And that should work for the DFS. And now we can go ahead and use BFS and DFS to fill out the max flow. So we obviously have a total flow right now of 0. We haven't called anything. And we want to continue looping and constructing level graphs while it's possible, right? So while there is a path available from source to destination, we're going to constantly be checking if there are augmenting paths in that level graph. Remember, we construct a new level graph only once we deplete all DFS paths in a specific level graph. If the new level graph has no way of getting from source to destination, we stop, and we can return the total flow. So while we're doing the BFS, we're going to have a flow value return to us. So it's going to be source, destination. We're going to give it a really high minimum value for the flow along with our graph. We give it a really high value, so pretty much all edge capacities and flows are going to be less than this max val. And max val is currently a really large number. So we do that for int flow, and we want to continue doing these DFSs while its value is greater than 0, right? So while flow, we're going to add the total flow plus the flow of one DFS, and we're going to keep doing it. We're going to do another DFS with the exact same parameters, right? So again, the flow is for one DFS call. While you're actually getting a flow and DFS constantly, you're going to keep checking, right? As soon as you don't get a DFS call, you're going to reconstruct the level graph and then try again. If the level graph doesn't have any valid paths, it'll stop and return false, and we can go ahead and return the max flow value. So from here, let's go to this problem, and we can kind of see how we can apply it to this problem. So given a graph with n vertices numbered 1 to n and m undirected weighted edges, compute the max flow from vertex 1 to vertex n. The first line contains the two integers n and m. The next m lines each contain three integers a, b, c, denoting there's an edge of capacity between nodes a and b. This is really self-explanatory, so let's get that input really quick. So it would be number of nodes and num edges. And we can read that in. And we're going to have to resize a lot of the stuff that we're using, a lot of the data structure that we're using to accommodate for the size of our problem. So for the graph level and the level vector, we will have to resize to the number of nodes. So we can do a resize for level and also the vector. Or we can initialize the vector initially with that size. Right. So now we can get all the edge values. And that's going to be A to B to weight. And we're going to add the edges. One important thing to note is that these nodes are actually indexed from 1 to 2, while we're indexing everything from 0, or not 1 to 2, from 1 on, and we're indexing from 0 on, so we really need to decrement these values. And we can go ahead and add that edge. From here, we can now just call the max flow algorithm. Our source is 0, and our destination is num nodes minus 1, and we can pass in our graph, and we can go ahead and see if this works with our with this input. Cool. So right now it does work, but there's a slight optimization we could make, which is really important. Whenever we're performing a lot of these DFSs, right? In this DFS, we are checking every single possible edge out of a node. But what if we've already checked one of these edges, and we already have proven it to be a dead end, right? There's no use in checking it again, but that's what this algorithm is currently doing. There's a very simple optimization that can dramatically increase runtime or time complexity, improve time complexity by basically pruning all searches that already result in dead ends after checking them once. And that is how this next node index vector is used. Because we'll be using it, I'll go ahead and resize it right here. And I'll explain how this works. In this DFS, if it doesn't find an edge, right? In this for loop, if it doesn't find a valid path, I is going to increment. That's for a fact, right? So that means for the current level graph, no matter what, there is no use in checking that edge again. And that's kind of what the dead end optimization is based off of, right? So instead of checking this every time, let's start this value. It should be called next node index of our current node. Next node index of our current node has to be less than the size of the adjacency list, obviously. And we'll be increasing next node index of our current node. And remember, I was technically next node index of current node, so I'll just pass that in there. So let me explain what this is saying, right? In the very beginning, they're all going to be initialized to 0, right? It's going to tell us the first index in our adjacency list to start checking for path set. But if we see that 1 doesn't work, then we're going to increment that value. So for all DFS checks after that, we can just go ahead and start a next node index val because we know that everything before it was a dead end. And that's the huge optimization of this. Another thing we have to change is that we're going to have to, every time we construct a new level graph, this is going to be obsolete. So we just have to make sure to fill the the next node, vector to 0 every time. So that should, is it next node index? Yeah. So that should accommodate for constructing a new level graph. And we can go ahead and see if it will still work. Although it might not be apparent that, it's so much faster with this specific problem, but let's go ahead and copy and paste this code and see if we get the right solution. It seems to be doing pretty well so far. And it's accepted. So clearly our implementation works really well. It's really fast. Hopefully it made sense, and I hope you guys learned something from the video. Thank you.